Welcome to lecture 1 of MCS 507. MCS 507 is a course on mathematical, statistical and scientific software, or scientific software for short. Welcome again to this recording. Thank you for your interest in this course. The purpose of this pre-recording or of this recording is to advertise the course. The main part is actually talking about the course and a little bit my vision of what software is and what role it plays into our MCS program. So this lecture is scheduled for this coming 10 January. As I record this, that day has not yet come, but as you watch this, you may be watching this when you enroll later into the course. So welcome. So what is the course about? So the catalog description is one sentence and repeats essentially the title preceded by design, analysis and use. In a way, this is not a programming course in the narrow sense. So programming is unfortunately often narrowed to coding. And when you say that you're a programmer, the next question is, what language are you using? So programming these days involves many issues. Involves the design, analysis and use of software. Here are the prerequisites. So the prerequisites are from an older time and mainly intended for students in our undergraduate program. MCS 360 is an introduction to data structures course. So what this means is that you have an understanding of programming in the practical sense. But this course is also a computing course, so that's why this scientific is there. It's a course for mathematicians and also for statisticians. So equivalent courses would be symbolic computation or numerical analysis. So the main problem in symbolic computation is expression swell and normalization of expressions. So we may have very complicated expressions, and sometimes different expressions, do they represent the same thing and when? So that's the main problem for symbolic computation. In numerical analysis, we are worried about conditioning and numerical stability of algorithms. So computing and programming are not the same, but if you have a background in computing and are very much interested in using software, and these days if you do science and also very much anything advanced in mathematical and scientific and statistical research, you will have to use software. So in this sense, this is a graduate course, even for students who have a very modest background. So this will be the 5th time that I will be running this course. In the past, there have been graduate students here who had even difficulties reasoning about a loop and who did very well then in the course as well. So it matters more on your interests and your mathematical and scientific abilities. The bottom line here is that this course prepares for supercomputing, MCS 572, which I hope to run next spring in 2023. It is also a course that is on our computational science prelim. So if you are in our graduate program, in our department, then taking 507 and 572 could help you with your minor sequence. Passing these two courses will help you, or you can also take the prelim exam. The first bullet point here is that MCS 507 would fit into an interdisciplinary computational science and engineering curriculum. So if you are any scientist or engineer in our College of Science or in the engineering department and you need really software, then this course would also be very good for you. Supercomputing is very important, and I think there will also be something about parallel computing in this course. So at our undergraduate level, so this course in a sense is also open to advanced undergraduate students. So our undergraduate program, our MCS undergraduate program, lacks a course in parallel computing. So in a way, this course also hopes to make up for it. Okay, so in English we can take a word and use it in front of another word, or so software on itself and research, but you could say research software to say something about the kind of software that we're looking at. So we don't look in this course at word processing, for example, or databases. So we'll look, unless of course they would be scientifically relevant, but our software is research. But you could also turn the words around. You could say software research. So just as we look at numerical algorithms, numerical analysis as a valid field of study, the analysis of algorithms for continuous problems, we could also consider software as a proper subject. So in that sense, what is in red here emphasized is that studying software is actually also a valid topic. So in particular, one of the main results of my PhD dissertation was actually software. So as I came to realize only much later. So here is to make my case. There are a lot of academic publication venues. So in academia, journal publications matter a lot. The ACM, Transactions on Mathematical Software, is actually a journal of a very high reputation. There are a number of conferences, and actually the goal of this course as a graduate students is that you could go to this conference and understand very much what are the problems, or even better, that at the end of the course you could actually make a contribution to any of these conferences. So there are regional conferences and international conferences, some of which have proceedings. So the Scipy conference, the annual Scipy conference, Scipy stands for Scientific Python, has proceedings. There is the International Congress on Mathematical Software, which meets every 2 years. There is the Practice and Experience in Advanced Research Computing. And then there are the SIAM conferences. Now there is the upcoming SIAM conference on parallel processing. And this is a hybrid conference. So the first lecture on Monday is scheduled to happen online. The pandemic has actually presented us with some opportunities. So the SIAM conference is also a hybrid. So many of the lectures are actually open online, and as a student you may benefit from even free or reduced admission. So the parallel processing is also a separate research, but software plays a critical role in there. The SIME conference on parallel processing is where also there's a lot of attention on software. Also high performance conferences. So they are not listed here, but software also plays a role there. So the parallel processing conference happens every 2 years. There is also the SIME conference on computational science and engineering, happens every 2 years as well. So, and it gets at odd years, the parallel processing even years. Just to make the case that software is important as an object of research on its own. It's essential to do research, but also doing software research, not caring about research software on its own, but software research is important. So an important point of this course here is that you will be able to evaluate software also. So what is good software? So I've been running this course now since the first time was 2011. And if there is something that never changes, then there is that it always changes. So this is a rapidly evolving field. In particular, and at the time when I started teaching this course, Python came up as a very suitable language and environment and ecosystem for scientific programming. So there are 2 books here that I mention. I think the second reference might even be freely available online, the Elegant Scipy. In the last run of the course, this was a resource for me. Last time when I taught this course in fall 2019, I was using many topics from the Elegant Scipy book. The primer on scientific programming takes a gentler introduction. So if you are new to programming, then the first reference is strongly recommended. So there are plenty of resources available that will gently introduce you into Python. Python is, by the way, the first language that we are using here in our undergraduate program. But the world has changed, so now there is Julia. In this run of the course, I will spend quite some time on Julia. If you've taken numerical analysis the past 2 times in 2021 last year, then you should have had an introduction in Julia. If not, don't worry, it will come. So what we will consider is I mentioned scientific Python already, but I will also mention SageMath, which is a free and open source software system that is built out of several components. All right, so we have the purpose of studying software as a topic of research. We have content or the background. Sage, Scientific Python, and Julia, and their ecosystems. Now, what is in the course now? Here is an overview, week by week. So weeks 13 and 14 are lumped together. So the 13 numbers are roughly speaking, the themes for every week. So this is still copied from my fall 2019 run, with the exception that Julia is already introduced in the week 4. So I will start out with the introduction into the scientific Python ecosystem, but then we will also commingle with Julia, followed by parallel programming. One of the keynote talks at the SIAM Parallel Processing Conference, the upcoming one in February, is that there will be a talk on Julia as a replacement for message passing. So I may, when the time comes closer, advertise that talk. In red, there is the midterm, so week 8, end of week 8. So a midterm is unusual for a graduate course, but note that this is course that is on the computational science exam. So the computational science prelim. The midterm for me is an opportunity to test out some of the most important questions, some of the most important aspects and problems that I would be able to ask on a scientific prelim. If you're not interested in the scientific in the computational science prelim, then the midterm exam is just a take-home exam. So don't worry about this. So in the list of topics, you see various domains of mathematics. I learned a lot of mathematics through software. So there is computational geometry that is sitting there, and so I hope in that week we have also a computational geometry class, an entire semester course. But I hope that in that week I can kind of show what are kind of the highlights, what is the duality between a Voronoi diagram and a Delaunay triangulation. So there is excellent software to illustrate and demonstrate the key tools from the computational geometry world. So even if in our curriculum there is not enough time for you to have taken all possible courses, software often gives you a very quick, in a week or so, or even shorter, gives you a very focused approach to learning some new and exciting mathematics, very useful mathematics as well. So our National Science Foundation had the term, or they still have the term, transfer of technology. I think that software fits that description perfectly. So the expertise from one domain, say computational geometry, gets exposed to anybody who essentially needs it. That's also another selling point for this course. Now, I have a prescribed list of topics. As a graduate student, I would have nothing, I would prefer really that throughout this course you actually discover something that you really need that is critical for your own research interests. So this is in a sense also a project-driven course. So instead of a final exam, we will actually have the possibility that you study a particular software. So that brings us to the expectations of the course. In the first part, I'm assuming essentially that your background is very diverse. So you may have used Python, but may never have used Julia, or perhaps it might be even the other way around. You may have used, say, MATLAB, but you may never have used computer algebra. So it is a programming. It's not a programming course. It's a software course, but if you learn programming throughout this, and I hope you do, it's often good if you want to learn how to write a book, you have to read a lot of books. So if you want to learn how to write good software, well, look at how good software is being composed. And all our software that we consider is free and open source. So may the source be with you is kind of the motto of this course as well. So there will be several activities. So there is homework. For every lecture I will have exercises. So the exercises will be on the slides. The midterm exam could be another take-home homework collection. I typically have it in two forms. Either there is a time-limited version, which would kind of correspond to taking a computational science prelim exam. That would focus on, it's still open book, open computer, but you will have to know how to do certain things without a limited amount of time. The computer projects are most important, and I often learn also a lot from your project presentations. So most likely the last lectures will be reserved for project presentations. Okay, at this point in time I would pause a little bit, ask for questions. Allow me to take the opportunity now to emphasize the most important two aspects of what this course is. So this is a course that takes software as a research object, just like numerical analysis is a valid subject to do research in. You can do research in software development, in the study of software, how it is designed, how it is used and applied. That's the first important thing. The second important thing is that although there is a prescribed list of topics, the main goal of the course is that you can actually learn how to see how software fits within your research interests. And the benefit that you may have is that you can go to a research conference where software plays an important role, or that even better, that you can start to learn how to contribute to various free and open source software packages. So these are the most two important things about this course. All right, so there is in this first lecture there is some material that you will need to know. So the middle part in this lecture concerns the three main environments that we will consider. So there is Sage or SageMath. So Sage used to be software in algebra and geometry. It has involved. So I learned about this project in 2006 when it was kind of starting to get somewhere. So the Sage project is presented in this, so I mentioned the International Congress on Mathematical Software. Here this comes from the Proceedings paper. The picture says it, so software that is useful. So we've seen numerical analysis. So in numerical analysis we study algorithms, but in solving a problem you actually need many algorithms that are combined together. But if you want to solve actually really hard problems, you must also combine softwares. So Sage bundles a lot of state-of-the-art software problems. So you see GMP, MPFR. So GMP is the GNU multi-precision, and MPFR is a wrapper on that. So the wheels are actually the arithmetic that drive things a little bit. So it's a metaphor. The assembly on how software is combined. Studying Sage, as Sage is also an example of a great software engineering project. So if you are a computer scientist, as many of you I think are, then what is now a good example of a large software? Well, Sage is one. So a free, so there is a VICE, so there are the big M's, Magma, Maple, Mathematica, and MATLAB. Sage has succeeded in building a viable alternative. So these big M's, nothing bad is to be said about this, and if you ever get the opportunity to interview at the MathWorks or at Wolfram Research or whatever, then please take that opportunity. There is nothing bad said about commercial software, but as an object of study, free and open source, there is a lot to be said for this. There is also an opinion. So the bottom line here is that if you want to do free and open source, if you want to have that your research is also open. So there is the free and open source research software. But if you want that your research itself is open, that people can use and reproduce your result, then using free and open source software is also, I would almost say, a prerequisite for this. So that's also what more or less is in the opinion. I mean, the date is 2007. I'm not going to claim that I just summarized that opinion piece, but this is my take on what I remember for this. Important community. If you want to solve important problems, you need to collaborate, need the help of others. And the others can be others separated from you in space, in time. It could very well be that the efforts of what somebody did 10 years ago may benefit you, or the stuff that you will be doing for your doctoral dissertation will benefit most likely people down the road. Installing software can be a frustrating activity. We are living now in the time of cloud computing. So the first exercises here are install or try online. So there's CoCalc. CoCalc is gives you not only the software itself, not only the software itself is free, but also the computing time to compute. So that's also very important. There are portals, also scientific portals, that give you access to supercomputers. So that's then more for the supercomputing course. But just to try things out, there is CoCalc. All right, so here is another picture. So there is the car, but then there is the alternative. Python is a framework language, which means that it comes with batteries included, and it is extensible. If you would say, what is Python? Then some people might say it's a gluing language. It's a language that glues several areas of computing together. So there's the core Python, then there is the enhanced Python, the Jupyter Notebook, there is NumPy, the Cython. So some people may say that Python is slow and therefore shouldn't actually be used, but there is the way to generate C code, or there is the version of Python which is typed and closer to C, so that is Cython. And then there is the Jupyter Hub, the tools to turn your computer actually into a server. So that's the second layer. Very close to that second layer is SymPy at one end and SciPy at the other end. Scientific Python. So scientific Python can mean the entire ecosystem, but there is also the SciPy package, just like there is the SymPy package. There is Matplotlib. I would say that if you have Python, NumPy, SciPy, SymPy, Matplotlib, then you have already the core of what is a scientific software system. Perhaps people will say it's a scientific software system of 20 years ago. Now a scientific software system needs a lot more than these capabilities, but the difference between a language, so extending Python with these packages, is straightforward. So the difference between what it means to programming often means you use the primitives provided by this language, but the primitives in Python with the extension start to blur from what is a scientific software system. So what we will do in this course, you could also say that what we do in this course is actually explore this stack, starting from Python, NumPy, SciPy, SymPy, Matplotlib. We go into Pandas, scikit-learn, scikit-image, and then something about PyTables, NetworkX, etc. Depending on where your interests then are going, there are many specific packages in science and mathematics which are not listed here. So this is in some sense also a dated picture. All right, so the SciPy community is extremely large. So here are the names of the people who made the first version of SciPy. There are the annual SciPy conferences, which is a gathering of many people who make contributions to the ecosystem. So I mentioned already the reference elegant SciPy. I mentioned here below. So there is the description in this textbook that gives kind of a sampling of many of the capabilities of this ecosystem. All right, so we have Sage, we have SciPy, and then there is Julia. So Julia is a project that is already also 10 years in the making, but only in the last 4 or 5 years came up at a more grander scale. So what does Julia promise to do? It promises to provide one language for prototyping, for which Python is really great, and also giving the close to optimal performance. It wants to languages such as Python are rapid prototyping, and it's very relatively easy. I mean, people who are in our first introduction to computer science language programming may disagree with this, that Python is easy, but if you come from the compiled languages, then Python makes your life a lot easier because of all its built-in tools. So what is important in Julia, that it is combining, so we will so I'm now a little bit hesitant how technical I should go. We will also address vectorization. So the fact that Python is slow is not entirely right here, because you see, indeed, when coded well, it can be very fast. So this is also true for Python when you have Cython and when you're using the vectorized code. Python has a nice syntax. If you do it well, then you write very short code and it's very adaptable. So this is a selling argument for Python, for Julia in a picture. There is the reference, the SIME review paper, which brought out to me also the language Julia, so now 4 or 5 years ago. In 2019, I had 1 week in which I considered Julia more towards the end of the course. Now I plan to put Julia more already in the 4th week of the course. Julia as a language, so it executes as a scripting language. So in the beginning, when I was looking into Julia, I was seeing Julia as an alternative scripting language to Python. This is not true. It is actually compiled. it's a programming language. What is true still, so the title of this slide is still correct in the sense that you can write highly performant code with the ease of a scripting language. Okay, so this is Julia in a nutshell. All right, so summarizing now, what is software? What is modern software? As a mathematician, I should actually have given a definition more formally. But let me, what does it mean to be a software now? Any software must interact with its users. So if you provide a scripting interface to your software, you give your software, you allow that the users actually can participate. So it's no longer a one-sided, guided, determined, fixed interaction, but users have control over the flow of computing. So there is the interactive computing that engages your user community. Once I was at a talk, and a senior researcher in biocomputing said that in his community, you don't install software. You just go to a website, you create an account, and you run things. So any software that is modern must have a web interface. So it must be available to your users without installation. So that's another feature that one would now expect from a modern software system. And then there is the entire issue of parallel computing. All computers are parallel. All computers are connected to the internet. They have several cores on their CPU, and every computer has a graphics card that is often already more powerful than the CPU. So we have a course in Introduction to Supercomputing where I try to address this issue, but also from a software perspective. What does it mean to be a modern software? It means that you must be able to leverage the hardware which is parallel. So your software must be able to communicate to other computers, must take advantage of the multi-core, and preferably also must be accelerated by the graphics, or must support massively parallel computing. So that means as a programmer, making software is kind of a daunting task, and it's not something that you will do in a short period of time, with the exception that software is generally not constructed from scratch. So what the course also should help you with is to find the components of the software that you will need. And from there on, you can build your own version. All right. There is then one appendix. Appendix, I shouldn't really say it like this. Let's do some calculation now. I've picked one of the algorithms that is the PSLQ integer relation algorithm, kind of as an illustration of what is available, and how you can use software also to learn more about mathematics. So we have to start from somewhere, and let us start with the arithmetic. So there is the exact arithmetic. There is then the floating point arithmetic. So it's natural that you can go from an exact formula and approximate this, but you can also go the other way, in the other way. So you have an approximation, you can find an exact representation. So that is what the PSLQ algorithm does. It is based on detecting integer relationships. So at its core, what it does, it finds, so given some real numbers, it finds an integer relation between these real numbers. So the real numbers are given with limited accuracy. So it is a hybrid computation as well. It involves arithmetic. So one can see the computations as starting with the arithmetic. It involves least squares. I will not go into details how this algorithm works. Feel free to look into the references. I hope that also learning mathematics through software is that it piques your curiosity and that you want to know how does it actually work. So a hybrid form of computing is working with algebraic numbers. So there are the rational numbers, there are the real numbers, but in between you have numbers which are algebraic. So they are roots of polynomials. And we all know the square root, we have a special symbol of this. You can also actually make, like here on this slide, you can make a symbol for the cube root of 4. And you can take it and make an approximation for it. But what you can do with PSLQ, you can verify, or if you have a real number, you can compute the closest algebraic number to this. You can find the polynomial, the smallest degree polynomial for which your floating point number is a root, is an approximate root. So once you do that, you actually go from the approximate computation, or numerical analysis algorithms that by default work with floating point numbers. You can flip your computation into a computation with algebraic numbers, which is then again an exact computation. So here is how it is done. So this is a Python 3 script. So there is the multi-precision math package that exports the PSLQ algorithm. 2 instructions. We have the 64-bit approximation for the cube root of 4. And then we can recover with the PSLQ algorithm, giving it the sequence of powers. And it will discover the coefficients, the integer coefficients of the polynomial for which the given approximation is a root. So you can do this in a Python session with the MP-math package. It's also identical in SageMath. All right. Here is a kind of a very interesting application. There are formulas that are giving you the expansion for pi. So the pi is not a rational number, not an algebraic number. So its expansion goes on forever. But you can compute the hexadecimal expansion in pieces. So normally when you compute a decimal expansion of a number, you're using some kind of Newton iteration and you expand and you extend the decimal expansion. Here actually with these Pigott formulas, you can compute one piece independent of all the rest. So this is important for testing algorithms, but it's also on its own. It's interesting as a mathematical curiosity. So this is an application of this integer relation detection algorithm. So you see here the formula, and since I have been rambling on the slide for a while, you may have memorized by now the coefficients 4, 2, 1, 1, or rather 4, -2, -1, and -1. We can recompute these coefficients. So here it is. We are running PSLQ again, and now in a separate Python script. So Python script that I may post. So this is running on the command prompt as a program with a list comprehension, a double list comprehension, where we compute a sequence of numbers and we feed the sequence to PSLQ. So essentially asking to compare, so we are solving again an equation where we are computing the coefficients of this expansion. So the result can be interpreted as the coefficients in this spigot formula for pi. Alright, so this is an illustration of what you can do at the arithmetic level with one built-in package, MCS, and the PSLQ algorithm that is exported by this module. There is a last exercise that asks you to experiment with this. But what is most important for this lecture and also for this first week of classes, so I'm taking into account that this lecture may be viewed by people who sign up rather late, so even if it's after the first week, what we essentially are going to do in the first week is trying to get familiar with the Python environment. So you can install everything on your computer. So the saying goes, may the source be with you. I'm still of the generation where I like to have all my software running locally. But in this day and age of cloud computing, everything can be, you can experience this course without ever having to install some software. So all software that we are using will also be available online. Alright, so again, thank you for your attention. So I am available for questions and comments. So in a way, everything will be, I will keep on continuing making these pre-recordings throughout the semester, even as we will go in transition in person. So this course can also be experienced synchronously. So if you do have a conflict in your schedule, you can also take this course, follow the pre-recordings, and contact me when you have problems. So again, why would you then take the course if you can just look at the pre-recordings? Well, by taking the course, you have access to me. No offense to people who are interested in this material and who are watching this. When you send me an email question, unless you are my student, I can't really guarantee you a reply or help. So taking this course has the main benefit that you get feedback on your homework that you submit, that I will give you feedback and suggestions on the projects. If you ever run into problems for your research for software, I'm more than willing and more than happy to help you with this. So thank you for watching this recording.